So in this lesson, which is problem set 63, what we have is that we're going to be simplifying square roots, and we're going to be doing that by recognizing products of square roots and a rule that goes with that. So if we look at this example, square root of 50, what we can recognize is that, yeah, we know that we can't write a value for that. That's not going to be an irrational number. 50 is not a perfect square, but we can write 50 as a product of two square roots. So what I might do to demonstrate this, say, okay, well, we could write 50 as 2 times 25, like so. And the reason that I picked 25 is because that is a perfect square. And then we can actually rewrite that again as the square root of 2 times the square root of 25. And when we do that, now we have something we can simplify a little bit, because the square root of 25 is 5 times root 2. And oftentimes how we'll rewrite that is that it could be simplified to 5 times the square root of 2, like so. Now, we could keep going with some of these examples, but we can also use prime factorization to help us as well. So if we look at this down here for this example, square root of 200, we could absolutely write that as the square root of 2 times 100. Again, picking 100 because it's a perfect square. And then, of course, write that as the square root of 2 times square root of 100, which allows us to actually get a nice integer square root. Square root of 100 is 10. So then we have kind of a similar situation to what we had before. But I want to kind of show you an alternative method for approaching this. Another way that we could do that is we could write the prime factorization of 200. Again, going back to our factor trees. And recognizing our pairs of values. For example, 2 times 2, 5 and 5. And if we have pairs of values there, what that allows us to do is to recognize that I can actually get integer square roots out of these two values, right? The square root of 2 times 2 would be 2. And the square root of 5 times 5 is 5. I can't do anything with that 2, but what I can do is just leave it under the square root sign and then get 10 times the square root of 2. So that's just another way to do these types of problems. So you can see that these two answers are the same, just two different ways to approach it. All right, so why don't we try that with 108. So I'm actually going to do the prime factorization method here, 108. Okay, so we got 2 2s, 2 3s. So if the square root of 2 times 2 would be 2, and the square root of 3 times 3 would be 3, and we can't do anything with that other 3, but we can leave it in the root sign. And if we just do 2 times 3, that gets us 6 root 3. So there you go. Product of square roots rule is essentially recognizing that we can simplify square roots that are not perfect squares. Okay, second part of 63 is that we have fractional equivalence of repeating decimals. Just as a reminder here that the way that you change a decimal to a fraction, or excuse me, a fraction to a decimal, is to divide the numerator by denominator. So we could take 1/3 and write it as 1 divided by 3. And when we do that out, what we end up with is 0.333, etc., also known as 0.3 repeating with the line over the top. If you do 2 divided by 3 and you do that out, what you'll find is that you end up with 0.666 repeating, also known as 0.6 with a bar over the top, indicating that 6 is going to go on forever. With 1/9, similar situation. You do 1 divided by 9, and what you find is that that actually ends up being 0.111 or 0.1 repeating. 1/6, again, 1 divided by 6, which equals 0.166, etc., and that can be written as 0.16 repeating, with a little repeat mark over the 6. That's the one repeating digit. So take a look at the problem sets for that A to D on page 259, and that's it for 63. Okay, changing gears just a little bit here in problem set 64. We're looking at domain and the additive property of inequality. So we're going to talk about the domain for an equation or inequality and the set of permissible replacement values for the variables in an equation or inequality. So I'm going to walk you through this, and I think that we're going to hopefully kind of see how this all fits in fairly quickly. This part says graph x is greater than 2, and then we've got d equals reals, or the set for the domain is all real numbers. So if we're going to graph this, we're going to be talking about graphing inequalities on a number line. Just have the x there. So typically I'll put a few values on there, 0, 1, 2. It should be perfectly spaced theoretically. There we go. Now if x is greater than 2, that means that 2 is not part of that set, so we put an open circle on that. And then what we do is that we'll send that where are all the values greater than 2? Well, they're to the right of 2, so we'll throw a little arrow like that. Now, because it's all real numbers, anything over here falls into that real category. That was back in problem set 61, where we were talking about what real numbers are. Anything over here, all the way up to infinity, is going to be a real number. Let's take a look at the next one. For this one, it's a little more complicated. It says graph x is not greater than or equal to 3, and our domain this time is just integers. So we're going to have to interpret this. To begin with, I don't really like talking about what x is not. So I can kind of figure out what x is based on this statement. X is not greater than or equal to 3. Well, then that means that x has to be less than 3, not including 3. So that's a little bit easier way to think about that. And the domain is just integers. So we have to be really careful here. What I'm going to do is I'm going to draw my number line here. I'm going to make sure that I have a few values, important values here. Maybe I'll start at -1, 0, 1, 2, 3. And we have to be super careful again because we know that the domain is just integers and it's less than 3. So 3 is not included, but nothing between 3 and 2 is going to be included either because all those values in between are not integers. So 2 will be included, 1 will be included, that's another integer, 0 will be included, -1 will be included, etc. And that would continue on. So again, because the domain is just integers, we can't include the spaces in between because the spaces in between these values are not integers. All right, let's look at the next one. This time we've got graph x is less than -1, where the domain is equal to positive integers. So let's think about this here. I'll sketch my little number line here. I'll make sure that -1 is on there, and maybe I'll put a couple before and after here. And I say, okay, x is less than 1, so that's everything to the left of 1, but then my domain is positive integers. Does anybody see the problem here? That's right, it's not possible for x to be less than -1 and be positive integers. So in this case, what we would write is that this is a null set. There is nothing that satisfies this set, and that would look like this, would be the empty set sign. All right, let's take a look at the additive property. All right, so this is a very similar type of question. The only problem with this one is that it very inconveniently has not been solved for x. So what we've got right now is x plus 2 is less than 0. So just like with equations, a really handy thing about inequalities is that we can solve them using something called the additive property. We can add -1 to each side, and it's not going to change the inequality, or it's going to create an equivalent inequality. So what I'm going to do then is I'm going to add -2 to each side, and I'd get x is less than -2, because if x plus 2 is less than 0, then that means x has to be less than -2. And our domain is equal to all reals. If I was going to graph that again, I go to my number line, sketch one of those in. I'm going to make sure that -2 is on there. I like to throw a few to the left and to the right. It is less than -2. It's all reals, so I can put an open circle on -2, and everything less than -2 is going to be down here on the left. All right, I got another one here. At the top, last one of the set. So we have graph x minus 3 is greater than or equal to -5. Not solved for x inconveniently, but if we just add a 3 to each side, that'll keep it equivalent. Just erase that there. So what I get is x is greater than or equal to, I don't like that, struggle bus. X is greater than or equal to -2, and our domain this time is all integers. So I'm going to, again, sketch my number line here. I'm going to make sure that -2 is on there. And again, find -2. It's going to be greater than or equal to -2. So because it's got that equal to, I definitely have to have a point on -2. Now it's just integers, so it's just all the values that are going to be greater than -2 or equal to -2 that are integers. So we're just going to put points on each one. Everything in between is not an integer. So give these problems a shot and see how you do.